Okay, this is section 4.1. Hopefully you recently watched section 3.5 because that is really a warm-up section for dealing with the normal curve. So let's dive in. So topics to take note on: the normal distribution, which has its properties, its notation, and then a z-score. Like what is the concept of it? What is the formula? And then percentile, and then computing percentiles from z-scores, which is we can use R or a table in the back of your book. And there's also other ways to do it. Like there's a way to do it in Excel too, but we'll mostly focus on using R and using the table in the back of your book. Also, how to do it the opposite way. Okay, which will make sense once we get there. All right, first, the normal distribution. So think about the words we learned in section 2.1 about how to describe a distribution. The normal distribution is unimodal and symmetric and is often called the bell curve. So many variables are nearly normal. Nothing is exactly normal, just like there's lots of things that look like circles, but there is no exact circle. So our notation is capital N and then two numbers, mu and sigma, mu being the mean and sigma being the standard deviation of the distribution. So heights of males. So OkCupid allows researchers to look at the data of people on their site. Sorry, I went too far ahead. So we have the soft line in the background is the actual heights of males based on scientific surveys, and the heights of people in OkCupid of men on OkCupid tend to be shifted a tiny bit to the right. So there's you can also see how instead of it looking normal at the top, you see that a lot of there's a rounding to 6 feet once you get pretty close to it. And then heights of females has a similar but not as strong thing as well. Okay, so that's just a little fun fact for you. Let's move on to the mathematics of the normal distribution. All right, so here are two normal distributions, and n with mu equals 0, sigma equals 1, and n with mu equals 19, sigma equals 4. And so if you notice the one on the right here, notice how these numbers are different from these numbers, and they're also scaled differently. So centered at 19, so it's centered at 19. And then notice how it's jumping by 4s on the tick marks in the bottom, whereas on the left it's jumping by 1. So if we graph both of these in the same window, they look like this. So let me erase it, I'm drawing too much. So here's each of them zoomed in a particular way, and then here's each of them in the same graph. Now, both of these, the normal distribution always has the area under the curve, like this area right here, that's always equal to 1 because it's the probability distribution. Okay, so SAT scores, let me move myself down here. SAT scores are distributed nearly normally with mean 1,500 and standard deviation 300. ACT scores are distributed, normally distributed with mean 21, standard deviation 5. So a college admissions officer wants to determine which of the two applicants scored better on their standardized test with respect to the other test takers. Pam, who earned 1,800 on her SAT, or Jim, who scored a 24 on his ACT. So look, once I put those on each of their normal curves, you already see who did better, right? So we see that if we put them on the same curve, we standardize both. If we standardize both of those normal curves and put them on the same curve, then we can say, instead of measuring actual points, measure how many standard deviations away from the mean each of them is. So Pam is exactly 1 standard deviation away. And we can find that by taking her score minus the mean for SAT divided by standard deviation. And that tells us Pam is 1 standard deviation above the mean. We can take Jim's score. So that's Pam's score. We can take Jim's score of 24 and subtract the mean for ACT, and then divide by the standard deviation for ACT, and we get 0.6. Jim's score was 0.6 standard deviations above the mean. Okay. So we call that thing we just computed the z-score. It is when you take your observation, which is like x sometimes, minus mean, which is sometimes written like x bar, and standard deviation, which is sometimes sigma or s. So another way to write this, oh, my handwriting's bad because I'm reaching across and trying not to spill my coffee. All right, so equals x minus, remember we have like x bar could be our sample. So if we sample and we want to find the z-score over standard deviation of a sample is s, right? And there's also, if you have perfect information, then it'd be x minus mu over sigma. So I'll put approximated by x minus x bar over s. So when you have perfect information, you do the z-score with your perfect information, x minus mu divided by sigma. And that's a good approximation. If you don't have that information, is your sample mean and sample standard deviation. Okay, so z-scores are defined for distributions of any shape, but only when it's normal do they really mean anything. And so notice that anything beyond 2 standard deviations away from the mean is super unusual. Let's go back. So anything outside 2 and -2 is fairly unusual. Most of the probability is inside there. Okay. So percentile is percentage of observations that fall below a given data point. So area to the left of that data point. Okay. So graphically, percentile is the area below the probability or to the left of that observation. Okay. So there's a couple ways to compute percentile of a normal curve. You could do calculus. Your problem with, you could figure out, I could tell you what, there's actually a function that gives you the normal curve. I could tell you that function, and then you could do calculus. The problem is, even if you're really good at calculus, that integral is impossible to solve algebraically. So you need a computer to do it. You need to approximate it. So there are different ways to approximate it. You can do this equation in R. So P norm 1800, mean equals 1500, SD equals 300, and it gives you the number. Boom. Or you could go to this applet from UCLA, and it'll compute it for you. Or you could go to your textbook and right here, and you could go, so this is a table in the back of your textbook. So it's, let's see, appendix. So it is, let's see, that's the T whole squared. There it is, page 410 and 411. So this is basically what I have in my slide right there. It should look exactly like page 411. So if you're looking on page 411, you go the first decimal place. So if I'm looking for, say, 1.00, which was Pam's z-score. So Pam had 1,800. We computed her z-score, and so then we got her z-score is 1.00. So 1.00 tells us it's this number. Okay, so that means that the Pam's percentile is 84.13%. So Pam scored better than 84.13% of the SAT test takers. There's this term called Six Sigma, which is, it's an industrial engineering term. It comes from the notion that if one has 6 standard deviations between the process mean and the nearest spec limit, practically no items will fail to meet specs. Okay, and you can follow that link if you're curious. All right, let's do a example. A Heinz ketchup factory that amounts, at Heinz ketchup factory, the amounts which go into bottles of ketchup are supposed to be normally distributed with a mean 36 ounces of standard deviation 0.11 ounces. Once every 30 minutes, a bottle is selected from the production line and its contents are noted precisely. If the amount of ketchup in the bottle is below 35.8 or above 36.2, then the bottle fails the quality control inspection. What percent of bottles have less than 35.8 ounces of ketchup? Okay, so we're going to solve this together. So first, let X be the amount of ketchup in a bottle. So X is like our probability variable, and the squiggle tells me that it is a normally, like it matches a normal distribution with mean 36, standard deviation 0.11. Okay, so we got to find the z-score for 35.8. If I graph it, let me move my head out of the way. If I graph it, then a normal distribution centered at 36 with 0.11 standard deviations, 35.8, looks right there. So let's do the z-score. All right, I want you to pause and do the z-score yourself. Okay, if you're just skipping towards the answer, you're going to miss out on learning. So pause, and I'm going to give you the answer in 3, 2, 1. Okay, so the z-score here is X minus mu divided by standard deviation divided by sigma. So our z-score is negative 1.82. Okay, so then we compute the percentile, because the original question is what percent of bottles have less than 35.8 ounces? So what percentile does 35.8 correspond to? So I could do P norm of the z-score, I computed already, or I could do P norm of the original number, the original mean and original standard deviation. Or I could go to my handy dandy textbook, page 410 and 411, and say, okay, my z-score was negative 1.82, right? So that means I'm going to find it there. My percentile is 0.0344. Okay? So what percent of bottles pass the quality control inspection? Okay, so going back, we found that 3.44% are too low, have not enough ketchup. So, sorry. So, what percent actually pass inspection? Okay, so be careful. Try to decide which one you think it is. I'm going to give you the answer in 3, 2, 1. correct answer is 93.12. Okay, why is that? Well, let's check. We're looking at the good region in the middle. Okay, that's percentile of the upper number minus percentile of the bottom number. That gives us the middle number, right? So z-score of 35.8 and z-score of 36.2, they're percentiles. You calculate them in your book or on R, and the percentile for the 1.8 positive 1.82 z-score is 0.9656. The percentile for the negative 1.82 is 0.0344. Subtract them, you got 0.9312. Okay? All right. Let's do another example. Let's find the body temperature of healthy humans is distributed normally, nearly normally, with mean 98.2 and standard deviation 0.73. What is the cutoff for the lowest 3% of human body temperatures? Okay, so we're looking at this. Okay, so now we have the percentile. We need to find the z-score. Okay, so we need to look up, we need to do a backwards lookup in your textbook. So we would go to your on page 410, and we would find the number on the inside. So this a backwards lookup. So I'm looking, instead of looking for the z-scores, I'm looking for the number that is closest to 3% or 0.0300. The closest number is 0.0301. So I'll pick that one. So that corresponds to the z-score of negative 1.88. So that means my z-score is negative 1.88. So then I got to find the x. All right, so we got to do some algebra. All right, so algebraically, I have this equation, z equals x minus mu over sigma, right? And so I know z, I know z is then negative 1.88. And I know mu is 98.2. And I know sigma, that's 0.73. Okay, so how would I solve for x? Well, I would do it like this. I would multiply times both sides by 0.73, add 98.2, you get, oh wait, I haven't even done that yet. All right, so that's just saying what I already wrote in a nicer fashion. So multiply both sides by 0.73 and then add 98.2 and you get 96.8. Okay, so this is from a paper, a research paper, in case you're curious. All right, let's do another practice. So body temperatures of healthy humans are distributed nearly normally with mean 98.2 and standard deviation 0.73. What is the cutoff for the highest 10% of human body temperatures? Okay, now I want you to pause your video. You should pause your video and actually compute this, okay? Okay, hopefully you paused your video and you tried to do, at least attempted this in some way. It's through struggle that you remember things. If you did not pause to do this and you just wait for the answer and you think, Dr. Johnson, I just don't remember anything from your slides. And I'll say, because you're not pausing. All right, so the answer is 99.1. And let's talk about the reason why. Start off with this normal curve. We're looking for the top 10% of body temperatures. Okay, so then we got to find the z-score. Okay, so you do your backwards lookup. Well, first, we're not even ready for the backwards lookup because what percentile does 10% on the top stand for? It's 90% on the bottom. So our your book, the table only looks up left sides. It only looks up percentiles. So if you're ever doing a right side here, you always have to translate it into the left side. So 10% on the right means 90% on the left. So now we're doing a backwards lookup for 90%. Okay. Well, I gotta find the z-score. Okay. So the z-score is going to be 1.28. All right. And you can find that if you look for the number closest to 90% in that table, it'll correspond to z as 1.28. And then solve algebraically. If x minus 98.2 over 0.73 equals 1.28, solve for x, you should get 99.1. All right. Okay. Now let's try, there's a couple heuristics about normal curves. So here's a quick heuristic, and it's kind of an older one from, before computers became really big, because this one's really easy to check. So you have some data, you say, is my data normal? And you can check, does 68% fall within one standard deviation of the mean? Does 95% fall between two standard deviations? Does 99.7 fall within three standard deviations? Then maybe it's normal. Okay. SAT scores are distributed nearly normally with 1,500 standard deviation. So that means you should have 68% are within one standard deviation of the mean. So 68, more than 2/3 of students should have gotten between 1,200 and 1,800 in the SAT. 95% of students are should have gotten within two standard deviations of the mean. So that'd be between 900 and 2,100. And then 99.7% should have gotten within three standard deviations of the mean. So that's be between 600 and 2,400. Okay, now, one of the reasons the SAT is nearly normal and not perfectly normal is that there's a top score, and doing this, the normal distribution still has a tiny possibility even way out there. But in normal situations like a test, there is an actual cutoff because there's the highest score you can get and the lowest score you can get. Okay, let's look at another example. So here I have some data on the number of hours of sleep on school nights from, I don't know, it doesn't say. I think it might have been college students. So let's say, and our college students tend to be rounding to the nearest hour. So then we get this kind of weirder looking histogram. We probably should have just made our histogram been with 1 hour instead of half hours, but oh well. So the mean is 6.88 hours, standard deviation 0.92 hours. So then 72% of the data are within one standard deviation of the mean, 92% are within two standard deviations, and 99% are within three standard deviations. That should be 1, 2, and 3. Sorry about that. I'll fix that typo. All right, so it's nearly normal. Okay, it's off a little bit, but it's close. All right, let's do another practice problem. So body temperatures of healthy humans are distributed nearly normally with mean 98.2 and standard deviation 0.73. Did I go the wrong way? We already did this. Okay. Yep. So, all right, I don't know, mess that up. Anyway, that completes the our talk on the normal distribution.